Welcome to Electrical Engineering with Excel. Several years ago, I developed some Visual Basic for Applications code for a user-defined function that would take a number and return a text version scaled to the appropriate engineering prefix level with the SI prefix appended. I then wrote similar code to do the same for capacitor values, since they rarely use the SI prefixes Nano and Milli. I have now decided to consolidate both of those features into one user-defined function. The VBA code is available with a link in the description. I love using Excel for circuit design calculators. I draw the schematic of the circuit and have the schematic component values be dynamically linked to the calculated values. This often means the E-series function that I developed is used to return the closest standard value first. This engineering prefix function will take that standard value number and return the value to the nearest SI prefix level with the associated SI prefix and SI unit. Here are those calculated values being converted to strings linked to the text in the schematic. See, the capacitors show up in microfarads and picofarads. The resistors are in kilo ohms. In July of 2022, I developed my first engineering prefix function. It simply scaled the number and appended the SI prefix. It was so primitive you had to manually concatenate the SI unit to the string returned by the function. The new software incorporates the inclusion of the SI unit as an input argument. In January 2024, I developed a similar user-defined function tailored to capacitor values. Capacitor manufacturers and most schematics shy away from capacitors in nanofarads and millifarads. They usually split between microfarad and picofarad at various levels. The function has arguments to program the output where capacitors are either in picofarads or microfarads and not nanofarads. This is an effort to merge the two functions together. I found it silly to have both. They use the same math to determine the scaled number and the SI prefix. I'll be marking those old videos as obsolete. We are dealing with SI units, the International System of Units, internationally known by the abbreviation SI from the French.
Système international d'unité.
It's the modern form of the metric system and the world's most widely used system of measurement. It's the only system of measurement with official status in nearly every country in the world, employed in science, technology, industry, and everyday commerce. Here is a list of the base SI units. The second and the ampere are the two foundations for electronics. The rest of the SI units for electronics are derived with these units, along with the meter and kilogram. Here's a complete list of the 22 derived SI units. Here are the ones primarily used for electronics. They are derived from these SI base units. Here's a complete list of the SI prefixes. I didn't get the memo, but Rana and Quetta were added in 2022, representing 10 to the 27th and 10 to the 30th. Their negative exponent counterparts, Ronto and Quecto, were added in 2022 as well. I'll expand the software to include these, even though their magnitudes are not consistent with anything I know of that would deal with in electronics. SI engineering prefixes are exponent multiples of 3. The ones that are not multiples of 3 are hector, deca, deci, centi. After all, have you ever heard of a deca-ohm or a centavolt? So I'll remove these from the list I'm using. Now we have just the engineering prefixes, those with the exponent multiples of 3. What's being developed is an Excel user-defined function that takes in a number argument, returns the text version of the number scaled to the appropriate engineering level. The associated engineering prefix is appended, and an optional SI unit can be appended. Here's an example of input values and the numbers generated with the function and the SI prefix added. The following example represents the same input values with generated numbers, including the corresponding SI unit after the prefix. I've shrunk the list of SI prefixes down to the ones most commonly used in electronics here. They range from 10 to the minus 12th to 10 to the plus 9th power. Here's an example of component values calculated in Excel for circuit design with their associated scaled SI numbers, prefixes, and units. For example, an input of 4,420 returns 4.42K with the Greek omega added for ohms. Here it is linked in the schematic for a resistor value. We must determine how to scale the input to the appropriate SI prefix level. In this case, 4,420 was divided by 1,000 to get 4.42. It's easy in our heads, but how do we know that kilo is the correct SI prefix mathematically? Exponent multiples of 3 are cumbersome to deal with in a software algorithm. There's a better way instead of using base 10. We exploit the use of the base 1000 representation of the number. The exponents will be successive integers that can easily be used for programming. For instance, the log base 1000 of 1000 is 1. The log base 1000 of 10 to the minus 12th is minus 4. We can easily use the log function to determine the SI prefix level of a given number. Here's a chart of the complete list of SI prefixes and their base 1000 representations. The base 1000 exponents range from minus 10 to plus 10, making a total of 21, having 0 power in the middle, which is 1 and has no prefix. There's an integer for each level of thousands. We can take full advantage of the VBA string arrays to accomplish this. You're not going to believe how easy this is. Dimension an array called prefix string or prefix str. The array will need 21 indices, as we saw earlier. So let's start with quecto with a base 1000 exponent of minus 10. We will just set the prefix string array index to minus 10. Wrong. Array indices are integers starting at 1. We will start quecto at 1 and then continue with the rest. Notice the index 11 is null for no prefix. That's 1000 to the power of 0. We can just offset our numbers by 11 to select the correct prefix string. Take the log base 1000 of this small number and take the integer value of it. We get minus 2. 1.35 to the minus 6th divided by 1000 to the minus 2nd power is 1.35. We take the minus 2 and add the bias offset of 11 to get 9. The prefix string with the index of 9 is the mu character for 10 to the minus 6th. Then take our 1.35 number and append the mu character, and we have 1.35 micro. Let's do another example. Take the log base 1000 of 1,442,000 and return its integer value. We get 2. 1.432 times 10 to the 6th divided by 1000 to the power of 2 is 1.434. Take our 2 and add the bias offset 11 to get 13. The prefix string with the index of 13 is the M, uppercase M, for mega, the character for 10 to the plus 6th. Then take our 1.434 and append the M character, and we have 1.434 mega. This is really cool, but there's a problem we need to overcome. The VBA log function is base E. It makes my head explode. The beginner's all-purpose symbolic instruction code was developed in 1964. Its log function was base E, the natural logarithm. Nowadays, ln represents the natural log, and log with no specified base is log base 10. It's on scientific calculators that way, as well as Excel functions. But never fear, we can use our best friend, the logarithm base change rule. With this, we can change the log of a number with any base and change it into the log of any other base. In our case, since we have the log e function in VBA, the log base 1000 of x is equal to the log base e of x over the log base e of the number 1000. The 1000s level of the input values can be easily calculated that way. First, we need to take absolute value of the input because it could be negative. The log of a negative number is undefined. Then, taking the log of that positive number, we divide it by the log of 1000. As I pointed out in a shorts video, a number in VBA should never be declared as a single precision. Its precision is low and really only helpful to conserve memories in computers many decades ago. The divisor of 1000 should be a double precision variable. As an example, we could dimension a variable named 1_1000 as a double and set it equal to 1000. But this 1000 divisor has meaning. Most professional software engineers do not like this, but the type declaration for a double precision number is the pound sign, used at the end of the number. That takes the number 1000 into the calculation as a double, without independently dimensioning a variable for it. Then the integer of that result is taken, which represents the base 1000 exponent of the input value. The log of 0 is also undefined, but we'll take care of that in the code early on. I made a video recently about how capacitor values are rarely represented with SI prefixes of Nano and Milli. I gave my perspective on the factors causing this and the historical effects of it. This is the reason I built into the functionality to work around this peculiarity. Here's a clip of a datasheet from a chemic capacitor catalog. In ascending values, it switches from picofarads to microfarads, no nanofarads. All values below 0.1 microfarads are in picofarads. Here's another example from an AVX catalog. It is the same with values below 0.01 microfarads or in picofarads. In some cases, the microfarad switches to picofarads at 0.001 microfarads. I'll explain more on that later. Here's the syntax chart for my user-defined function. It has 7 arguments. The first argument is the numeric input, which is required. It's the number to be scaled and have the engineering prefix assigned to it. The second argument is the unit character. It's a string for the characters of the SI unit. It follows the SI prefix. The string would be F for farads, H for Henry, the Greek letter omega for ohms, and so on. The default is null. Although it's optional, it's rarely without use. The next argument is cap mode. When greater than 0, it does not return the SI prefix nano for a given input and provides an option for where the transition occurs between microfarads and picofarads. Next is skip milli. If true, it does not return the prefix milli. For instance, if the SI unit string is F, values in ascending order go from microfarad to farad. The default is false. You would not want to set this to true if it was being used for other units like voltage, as in a millivolt. Next is microfarad blank. If true, and if the prefix mu is calculated, mu is not displayed. This is useful when schematics indicate all capacitors are in microfarads unless otherwise noted. It's there to reduce clutter in schematics, and the default is false. The space separator if true, adds a space between the number and the prefix. The default is false, but more on that later. And finally, round digits. This rounds the result to a specified number of digits. -1 is no rounding, which is the default. 0 returns the integer of the output value with no decimals. 1 and up is the number of decimals to round, 2, 3, and etc. Of course, wouldn't you know it, there's a standard for spaces by NIST. Here's a chart from NIST with all the detail of how a SI prefix and a unit should be written. Here's the part showing where the symbol should be a space before the prefix and the unit symbol. I set the space separator argument to no space. That's the way I'm always going to use it. I like to save room on schematics. If you're a fan of the space, change the default. The world is your oyster. I guess NIST did not mind their spell checker. Space of any kind is valuable in schematic diagrams, so spaces between numbers and prefixes are rarely used. In fact, sometimes a prefix is spaced where the decimal should go. I decided to not make a provision for that. The rounding functionality is straightforward. The rounding digits specify how many digits to round. In some cases, the digits repeat forever and need to be rounded. However, all of the E-series component values are already rounded. Each number is rounded to 2 significant digits or 3 significant digits for the higher precision parts. In January of 2026, I posted a video of my latest update to a function that returns the closest E-series value of a given input. For schematic component values, the round function would never be required when the input value is an E-series component value. It's already rounded. Let's get into the syntax and all the arguments, specifically related to the special configurable capacitor modes. The function has 7 arguments. I sequenced them in the list in what I thought was most used first. All arguments but the first are optional. The first argument is the input value, a number that will get scaled and assigned the SI prefix. For demonstration purposes, I've made a chart to show what will happen with various number inputs conducive to the ranges of capacitance values. Each input comes from column A, here on the left. The values range from 10 to the -12 to 1, with the addition of a number in the last row that is in the microfarad range and has repeating decimals to demonstrate the rounding function. Notice this scales the number and appends the appropriate SI prefixes. Next is the unit character. Its default value is null. In this example, it's the uppercase F for farad. Notice it appends the SI unit farad to the end as expected. In a lot of cases, this is all you need. This third argument is the cap mode. It's an integer that ranges from 0 to 3. When the cap mode is greater than 0, it skips the Nano prefix. In ascending order of input value, the prefix goes from micro to pico. I'll set it to 1 in this case. Then everything below 0.001 microfarad is in picofarad, along with the skip milli argument, which is set to true. This skips the milli prefix and uses micro instead. Now for cap mode 2, everything is the same, except everything below 0.01 microfarad is in picofarad. For cap mode 3, everything below 0.1 microfarad is in picofarad. The next argument is microfarad blank. It does what it says. Everything that would normally be marked microfarad will be blank. With it set to true, here are the values with no prefix or unit. With the skip milli set to true, all the values that would have been milli are calculated to be microfarads, so they show up as blank as well. Notice the cap mode is set to 1. All values below 0.001 microfarad are in picofarad. This setting is most useful when you have schematics that indicate all capacitors are microfarads unless otherwise specified. It reduces clutter and makes extra room in the schematic. Now for the space separator and round digits. With the space separator set to true, it inserts a space between the number and the prefix or unit. The round digits is the number of digits to round the returned number after it has been scaled to the appropriate SI prefix. The input on the bottom left with all the trailing digits will be rounded to one trailing digit. Now the round digits is set to 3 and the output has 3 trailing digits. Now I'll run through an overview of the VBA code. This is the function statement, a very important one. The function name in this case is engineering prefix 2, which can be used like any other function in Excel. Here's some examples of formulas using this function. The argument list is separated by commas. As I explained earlier, this function has 7 arguments. With this long list of arguments, the command line would be quite long and would require panning across the editor to read it. In the Visual Basic editor, there's a way to wrap the line to make it more readable. Use a space, an underscore, followed by enter, and a new line will begin. Use the syntax optional for arguments that are not required but can be used. The first argument is the input value, which is required. Next is the argument name, then the data declaration. Use an equals sign to assign the default value of the argument, the value that is used if not specified. Data declaration of a Boolean variable means it's either true or false. At the end of the argument list, after the closed parentheses, can be the data declaration of what is returned by the function, in this case, a string. Comments in the code are essential. Use an apostrophe to comment. Any text following the apostrophe character on the same line is ignored by the compiler. This is the section to load the string array with the 21 SI prefixes. Dimension an array of 21 strings, 1 to 21. Assign the associated SI prefix in order. You can create the Greek mu symbol using the CHR command using the ASCII character for mu, which is 181. I'll limit the length of the unit character argument to a length of 3 using the left command. The arguments of the left command are the string name and the required length from the left of the string. Somebody might try to paste the entire content of an encyclopedia in here. The SIRAD for radians is the longest unit symbol. That's why I decided to limit it to 3 characters. To incorporate the space between the number and the prefix or unit, the space character needs to be selectively generated based on the space separator argument. Dimension the SEP variable as a string. Many who write software will write all the dim statements at the very first section of the code. As I gain more experience in coding, I've learned that it's a good practice to use the dim statement just above where the variable is used the first time. That way you or another observer doesn't have to look around for it. Use the if statement to see if the separator argument is true. If true, make SEP a space, else make SEP a null. The first calculation we do to the input value is take the log of it. The log of 0 is undefined. If a user inputs a 0 as the input value argument, the function will blow up. So to prevent this, use an if statement to see if the input value is 0. Then set the engineering prefix to function variable to 0 and concatenate the sep and the unit character variables and then exit the function. Define the microfarad to picofarad split val variable as a double. Use a case statement to see if the cap mode input argument is 1, 2, or 3. Do nothing if the case is 0. If the case is 1, 2, or 3, set the microfarad to picofarad split valve to the appropriate level to split between picofarad and microfarad. Case else is used to raise an error, since any other value between 0 through 3 is invalid. Use the error raise method with the VBA variable VB object error number. This is the base number for VBA errors. VBA reserves the first 513 error numbers as system reserve, so add 513 to the VB object error number, then exit function. Define the thousands level variable as an integer. Here's the math to generate the prefix as shown earlier. Define the prefix variable as a string. The computed prefix string array variable has an index of the thousands level plus the offset bias of 11. Dimension the output value variable as a double. And here's the scaled output value. It's the input value divided by 1000 raised to the power of the thousands level. If prefix is calculated as n and the cap mode is greater than 0, convert nano values to pico or micro. If the input value is greater than or equal to the microfarad to picofarad split valve, then divide the output value by 1000 to convert to micro and set the prefix to micro, the prefix index number 9. Else multiply the output value by 1000 to convert to pico and set the prefix to pico, the prefix string index number 7. If prefix is calculated as m for milli and the skip milli argument is true, convert the milli values to micro. Multiply the output value by 1000 to convert to micro and set the prefix to micro, which is the prefix string index number 9. If prefix is calculated as prefix string 9 mu for micro and the microfarad blank argument is true, set prefix, SEP, and unit character to null. That way nothing will be there to concatenate with the output value number. Declare the return value a string. If the round digits is less than 0, set the return value equal to the output value. In other words, no rounding. Else set the return value equal to the rounded value of the output value to the number of digits in the round digits argument. Create the engineering prefix to return string to be return value, SEP, prefix, and the unit character concatenated together. Then end function. This code will be available in the description of this video for you to paste into the Visual Basic editor. I hope you find it useful. Let me know in the comments if you do. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.